Pohang University of Science and Technology. So I'm going to talk about polymer gate dielectrics based on polymer silicon heterojunctions, and I'm going to talk about capacitance voltage measurement, and I'm going to talk about briefly about the gate insulators we tried, and then pentasen OTFT based on those insulators, and finally I'll talk about molecular layers for the improvement of interfaces and to make so-called nano-FET devices. Well, if you compare this soft material with hard material, there are some similarities. Also, there are some differences. So here you can see semiconductor insulator metal structure, so-called MOS structure for silicon devices. And before you make transistors, with this simple structure, you can evaluate the properties of insulators and also the interface properties of insulators and semiconductors. And this MOS structure is made from single crystal silicon and then silicon dioxide as a gate dielectric and metal gate electrode. This is a very important part of the transistor in silicon devices, and single crystal silicon is used, for example, for DRAMs and microprocessors. But if you move to organic transistors, we use organic films for gate dielectrics, and in this case we can make this structure based on the same principle with this MOS structure. For example, silicon single crystal, and in this case, fluorinated polyimide was used, and copper was used as a gate metal. And sometimes you insert thin layers of SiO2 to improve the interface properties. And when you talk about or think about molecular layers, you can also use so-called self-assembled monolayer as a gate dielectric. In this case, you put self-assembled monolayer on silicon wafer. Mainly you start with very thin native oxide, and then this molecule will react with silicon group on the surface, and then you will get a monolayer alignment, which can be used as an insulator. This is kind of a molecular device. And when you use this SEM feature, we can change the length, in other words the thickness, by changing the number of CH2 groups, for example from 10 to 15 or 20. And also we can modify surface properties by putting some functional groups at the end. If we have like a methyl or alkyl, then the surface will be hydrophobic. But if you put like COOH or some other hydroxyl groups, and then the surface will become hydrophilic. Professor Park and other people mentioned about the surface properties because that determines the morphology of the pentasen or other organic semiconductors growing on these molecular layers. Well, for silicon semiconductor and SiO2 insulators, it is well defined and well studied because silicon device has been in the market more than 30 years. Here you can see some charges or defects in the silicon and silicon oxide system, which will affect transistor properties. So we already know that there are different kinds of traps or charges. One is fixed oxide charge, which is located near the interface. And in this region, there is a transition between silicon to silicon dioxide. So this region is basically silicon suboxides. In this case, X is less than 2. And there are some fixed charge around this area. And also, interface trap charge is near the at the interface. This will affect the mobility of the carrier. So it is very important to reduce these interface traps. And this comes from the silicon dangling bond at the interface. So sometimes annealing or some other hydrogen passivation helps to remove this interface trap densities. And also we can have some mobile charges, for example, alkaline metals like sodium or potassium, which is really bad for transistor performance. And another thing is oxide trap charge. It's like electrons or ions trapped in the oxide film. So there are many charges and defects, and we understand already about those effects on the device. But if you switch back to polymer systems, I don't think we fully understand all those things. If you compare with inorganic counterparts, so I think we have to go a long way to understand those problems in OTFT and also problems with gate dielectric and also the interface, things like that. Well, if you measure capacitance with the sweeping voltage, basically you get this kind of graph when you use P-type silicon wafer and then SiO2. This is well-defined CV plot. In this region, the hole is accumulated at the interface because this is a P-type silicon. Then you get the maximum capacitance based on this oxide dielectric layer. And this one gives you the dielectric constant of the insulator. And if you sweep the voltage, then you get flat band voltage, so-called, and then threshold voltage. But if you have defects or mobile charges or some other fixed charges, this curve will change. I mean, the shape or slope or the position of this flat band voltage or threshold voltage. So by looking at this simple CV measurements, you can have some ideas about the defects and the insulators and semiconductors. We have been studying organic materials, inorganic materials like high K dielectric, which can replace silicon oxide. And this is hafnium oxide on P-type silicon, and this is lanthanum oxide on P-type silicon. If you look at the inorganic system, the inorganic material is quite stable and with less number of defects. So this flat band voltage shift from 0 is relatively small, usually less than 1 volt. And if there is a positive charge in the gate dielectric, the curve will shift to the negative direction. And if you have negative charge on the insulator, then it will shift this way. So sometimes you measure the CV plot after the annealing of the system at different temperatures and compare those curves. And you can see that this shift is really small for inorganic cases. And for group 4 metals, usually you have positive charges. And for plus 3 metals, you have negative charge in the film. This is mainly from the oxygen deficiency and defects from those kind of things. Next slide. This is a low temperature SiO2. Well, in MOSFET, usually SiO2 is grown by thermal oxidation of silicon surface. In the case, you have a very nice interface. But if you deposit SiO2 at low temperature with Teos ozone CVD, you can notice that there are some hysteresis and some irregular shape in the film. That is mainly due to the impurity in the film, mainly OH, silanol group, mainly from the water vapor remaining in the film, because if you deposit these things at low temperature, sometimes the water is not completely removed. So from this inorganic counterpart, you can get some ideas about the insulators and the impurities in that. Next slide. And if you have mobile charges in the film, then it will shift either into this direction or in the other direction, depending on the polarity of the charge. And from this measurement, we can measure the flat band voltage shift, which can give us the amount of mobile impurities in the film. This can help characterize the polymer films. Next slide. So we tried PMMA and so-called cyanoethylene. This polymer is quite popular for e-beam resist, but we tried as a gate insulator. And this copolymer is also quite popular. And this cyanoethylene has a polar group. For example, Xe here has ethyl cyanide. So it has a high dielectric constant. Usually PMMA has a dielectric constant about 2.6 to about 3. But this so-called cyano regime has a dielectric constant about 15, which is really large as an organic polymer material. And polyimide also is widely used. Professor Park also used polyimide as a gate dielectric in his transistor. And this one is poly-3-octyl thiophene. And these are the materials used as a gate dielectric to make organic thin film transistors. This one was done by Lee and Baraka in 1999. They tested fluorinated polyimide with silicon polymer metal structure, and they changed the voltage and measured the capacitance. Next slide. In this experiment, they annealed the film. They compared a film annealed below 350 degrees and a film annealed at above 350 degrees. And as you notice, there is some difference between this one and this one. The voltage was shift between negative to positive direction. As you can see here, the flat band voltage shift is about from -8 to -12 volt. That means you have some positive charge in the film, and the magnitude is quite high if you compare with inorganic silicon case. And also one thing to note is if you anneal at high temperature, for example above 350s, the shift is smaller. But if you anneal at lower temperature, there is a larger shift in this direction. So the annealing is also quite critical to remove these mobile charges. So in this case, higher the anneal temperature, you get a better film for polyimide case. Another thing is so-called bias temperature stress. In this case, you heat up the polymer and apply DC voltage. And then in this case, the mobile charge will move either towards the semiconductor or towards the metal. And then this CV curve will change. From this measurement, you can measure the amount of mobile charges in the film. Next. And another characteristics of organic gate dielectric is, for inorganic case, electronic polarization or ionic polarization is dominant. But for polymers, this dipolar group plays an important role in K value. In this case, if you change the frequency, then the dielectric constant will change because we are in this range. For inorganic case, it's quite stable and independent of frequencies, but organic materials, you have to think about temperature effect and also the frequency of the field. So let me introduce some of the results with this cyanoethylene polymers. As I told, it has a dielectric constant of about 15 at 1 megahertz. And degradation temperature is around 250. And the glass transition temperature is around 110, which is found from this DSC measurement. And usually you do spin coating from polymer solution. So we tried two solvents to dissolve this resin and then spin coat it. Depending on the solvent, the viscosity will be a little different. And then in this case, when you spin coat, the thickness of the film is also a function of the viscosity. And the viscosity also depends on the concentration of the polymers. So this one gives you the basic data for that. Next slide. And spin coating is quite simple. You just spin the substrate and then drop this polymer solution. So for PMMA and for CRS resin, the spin coating is done about for a minute. And after spin coating, you usually heat up to remove this solvent. This sample was dried in vacuum chamber for about 3 or 4 hours. Right? And this is what gives you the thickness of the film as a function of spin speed. Next. And the question is what is the optimum temperature for annealing? If you look at this temperature scale, there are different regions. Of course, the maximum temperature is the dissociation temperature. You cannot heat up the polymer near or above the dissociation temperature because this will break everything. Also you can think about glass transition temperature for polymers, and it is about 110 or 108 for PMMA and this cyanoacrylfluorine polymers. So the question is it better to anneal around TG or below TG or above TG, or how much above TG? Well, the common sense says that if you have to anneal probably above glass transition temperature, because then the chain will move to align. That's the meaning of annealing. But if you look at the results, that's not always true for different polymers. And we cannot say exactly why that happens. But so we anneal film at room temp, as deposited film, anneal around 70, annealing around 100 or 110 and 150 and 200, and compare the insulating properties of the film. And this one is PMMA. These two curves are from the sample annealed above the glass transition temperature, and these three are below glass transition temperature. And this capacitance was measured at 1 megahertz. Well, if you look at the flat band voltage shift, it is quite large, around 10 or 15. But if you anneal the film above glass transition temperature, it goes up more than 30 volts. That means we have more mobile charges here. So in this PMMA, the sample annealed at lower temperature shows better properties. If you compare the film annealed above glass transition temperature. And we don't know the reason why it happened for PMMA. This one shows CV curve of CRS annealed near glass transition temperature, and this is as a function of frequency. This one is for 1 megahertz. This one from few hundred hertz to kilohertz. And if you compare these two, this resin shows very small flat band voltage shift around the order of 1 volt. So this one has less mobile charge in the film. So it looks like this film is better than PMMA. Next slide. This one shows the dielectric constant as a function of frequency for PMMA. As you can see here, when the frequency increases, the dielectric constant goes down, because at higher frequency, the dipole simply cannot follow the change of the polarity, so the K value will go down. Next slide. This one shows the dielectric constant of CRS film. At low frequency, it shows about 19, and then it goes down to about 15. So this polymer has quite high K value. And this one shows K value as a function of the annealing temperature. Looks like there is a optimum temperature near the glass transition temperature. And if the annealing temperature is higher, the K value will go down. But it shows around 15 or 16 in this range. Right. And this one, well, from that semiconductor insulator metal structure, you can also measure IV characteristics. The leakage current through the gate dielectric. And this one shows you the electric field, and this one shows the leakage current. And looks like there is a jump in leakage current around 0.3 megavolt per centimeters. This one is for PMMA film, but you can see that the film annealed at higher temperature gives worse leakage behavior. The films annealed around 70 or S deposit film shows higher breakdown voltage strength. Next slide. And this one for CRS films, but in this case, S deposit film shows better insulating properties. Annealed film shows higher leakage current. So in this case, we cannot understand exactly what happens, because usually annealing helps the electrical properties of the film, but in this case, that is not the truth. So there are many difficult things to explain with organic dielectrics in this case. Next slide. This one shows you the surface roughness measured with AFM. And when you anneal the film, then roughness becomes higher, but usually it's in the range of 2 to 3 angstroms. The film is quite flat. Right. And then we made the transistor with evaporated pentasene film with the CRS, cyanoethylfluorine as a gate dielectric. This is grown at room temperature. This is at 70 degrees centigrade. Looks like the grain size is bigger here. Next slide. And also we measure the transistor characteristics. And this CRS resin has a dielectric constant of about 15. So we expect to get better transistor performance. For example, low threshold voltage and low subthreshold swing and high on-off ratio. And this is the level of leakage current. While the mobility is around 0.045, but we are not in a good environment to make a good transistor, so this one shows a little bit poor compared to other good results. But at least you can compare relatively with other, in this case we are going to compare with the CRS and PMMA. Next slide. So these are the values reported in the literature for different gate dielectrics, the mobility and threshold voltage and other transistor parameters. And we would like to stress that the CRS film with K value about 15 shows very low threshold voltage, comparable mobilities, and on-off ratio is quite acceptable too. Next slide. So, how many minutes do I have?
5 minutes.
And next one, I'll briefly talk about the molecular layer to improve the transistor performance. As you can see here, there are 2 different structures to make organic thin film transistors, and you have interfaces between dielectric and semiconductor, and also there is a contact between source metal and drain. For source drain contact with the semiconductors, pentasene is basically p-type semiconductors, so you need good hole injector, and gold is usually highly preferred. But as Dr. Lee mentioned before, the gold is expensive and also difficult to etch. So usually people use ITO as a source and drain metal. And in this case, we have a contact between ITO, inorganic oxide, and then pentacent organic molecules. So as Dr. Lee mentioned, we have all kinds of contact problems which degrades contact resistance and also transistor performance. So basically, sometimes the insertion of SAM layer helps this contact, and also this dielectric and semiconductor interfaces. So there are many ideas with different molecules to deposit self-assembly to improve the interface properties. Next slide. Well, this one shows pentacent morphology on ITO and on PMMA, on PVP. And the Dr. Park mentioned about surface energy and how surface energy affects the pentacent morphology grown on top of that. You notice that morphology is quite poor on ITO glass. So sometimes you need some treatments to improve the morphology of the pentacent. Next slide. Because of the time, I'll just skip some of the slides. Next slide. Next slide. Next slide. This is the contact angle measurement, which gives you the surface energy of the film. So you just measure the contact angle and then convert that into surface energy. Well, you can also do the same thing with self-assembled monolayer. For example, here people compared many different molecules with different functional groups at the end. Well, some functional groups are hydrophobic and some are hydrophilic, and it gives you all the different contact angle. That means the surface, we can control the surface energy by depositing self-assembled monolayer on the surface. Next slide. And the most well-known SAM system is thiol on gold. For example, if you react this thiol group on gold, you're going to have a surface reaction and then alignment of this molecule. So you can control the length by changing this N value here. And also you can control the surface property by changing this end group. Next slide. And well, for gold and thiol system, you can have a very well aligned with less amount of defect molecular layers. Next slide. And sometimes people mix two different SAM molecules. For example, one is long and the other is short. Then you can have all kinds of this covering of the surface, and then the side group will become the surface properties. So with those kinds of methods, you can play with surface properties on the film. Next slide. And this one is well-known example of treatment of insulating layer before you deposit pentacent films. Those are the molecules you try on, and then you change the mobility and everything. Next slide. You can notice that this one already shown by other presenters, but you can notice that the morphology can change by using different SAM molecules. Next slide. But you cannot believe SAM because you can have many kinds of defects or the particles and everything, and then you will have some leakage problems. So you have to make a very nice film and then characterize these things. Right. And some people make so-called nano-fat. They deposit SAM molecule on single crystal silicon and then pattern this with metals. And then gate dielectric is really thin, between 1 to 2 nanometers. And then measure the transistor characteristics. They call it nano-fat. And they tried different molecules with different function at the end. Next slide. They measure the surface group with FTIR with ATR facilities. Next slide. And they compare the leakage current with molecules with different function groups at the end. Next slide. And transistor characteristics. Next slide. So, as I told, same molecule can be used to improve the interface, but sometimes you can use it as a part of the device, like insulating layers. And this paper came from an article from published in Nature. This is the method. They treat the heavily doped silicon with chemical to make chemical oxides. Then you have OH group on the surface, and you treat with this kind of SAM molecules. Okay, okay. Here they argue that they have a benzene ring at the end of the molecule, and then they deposit pentacene. You know, pentacene has 5 benzene rings, so they argue that they have a very nice compatible interface, and they just use this as a gate dielectric, this molecule here, and deposit pentacene, and then make a transistor. Slide. And they measure the characteristics of the transistor, and they show it's really nice. Right. And they also measured IV characteristics with SAM and then gold contact and on silicon. And they said this breakdown voltage is about 14 megavolt per centimeter, which is really remarkable. Next slide. And they also measured some other types of transistors. And this is the end of my talk. Thank you.